Hello, I'm the mostly harmless Mr. Daycock, and today I'm going to be teaching you how to solve homogeneous second order recurrence relations. So what is a second order recurrence relation? Well, here we have an example of one, and it is second order because our next term, our UN term here, is dependent not only on the term before here, but also on the term before that here. It's got UN is equal to UN minus 1 plus 6 lots of UN minus 2. So let's see what that looks like. So our U1 here has been given to us as 0. And now normally that would be enough, and our first order ones that would be enough. But notice here, because we require 2 terms to get the next term, we also need to be given U2. So they've given us U2 as 1. And now let's consider what that makes U3. Well, U3 is the term before U2 in this case, because if we're dealing with U3 here, this must be U2, because 3 take away 1 is 2. And we also need to add on 6 lots of U1, because 3 take away 2 is 1. This is U1. So U3 is equal to U2 plus 6 lots of U1, which in this case is 1 plus 6 times 0, which gives us 1. So U3 is going to be 1 in this case. U4, well, now it's going to be U3 plus 6 lots of U2. So it's going to be 1 plus 6 times 1, which is 7. U5, well, that is going to be U4 plus 6 lots of U3. So it's going to be 7 plus 6 times by 1, which is 13. And then U6, exactly the same principle. It's going to be 13 plus 6 lots of U4, which is 7. 13 plus 6 times 7, and that will give us 55. And so we have our sequence here. It's going to go 1, 0, 1, 1, 7, 13, 55. And this here is our second order recurrence relation. And notice how it's kind of jumpy. Notice how we've got this 0 here, and then it jumps to 1, 1, and those are about the same. And then 7 and 13, they're about the same order of magnitude. And then it jumps again to 55. And the next one will be around the same order of magnitude as 55. Not exactly the same, but it's going to be about double it. About the same order of magnitude here. Now, our question is, how are we going to solve something like this? Well, all our recurrence relations before, well, the ones we were dealing with were generally of the form, they had some solution, general closed form solution of un equal to some c, some constant, multiplied by some r to the power of n. That was our general form, and we didn't know, and we could work out what r was based upon the terms here, our coefficients. But here we've got 2 coefficients. We've got one which is 1 and one which is 6. So we've got 2 coefficients, and so it's not as clear what r is going to be. So we're just going to try and see what happens if we pick un equal to c times r to the n. Well, similarly, we now to plug that in to see what happens, we're going to need to know what un plus 1 minus 1 is going to be. Well, that's going to be c times by r to the n minus 1, and which is c times by r to the n times by r to the minus 1. And r to the minus 1 is 1 over r, so it's c over r, r to the n. And un minus 2, well, that's going to be equal to c times by r to the n minus 2, which is going to be equal to c times by r to the n times by r to the minus 2, which is equal to c over r squared, r to the n. And now we have our 3 different terms that we can just plug in to our recurrence relation and see what happens. So we're going to get, plugging those in, c r to the n on the left hand side is going to be equal to 1 lot of un minus 1, so c over r, r to the n, plus 6 lots of c over r squared, r to the n. And like I say, that's 6 lots there. Let's make sure to put that in. There you go, 6c. Now this, again, seems incredibly complicated as an equation. Like, it's not going to help us at all. But actually it's going to help us loads, because what I hope you will notice is that in every single term there is this c times by r to the n. And assuming r is non-zero and c is non-zero, these are always going to be non-zero, so we can just divide through by them. So we're going to divide by c r to the n. And if we do that, we're going to end up with 1. Cr to the n divided by Cr to the n is going to be equal to 1. Cr to the n over r divided by Cr to the n, the Cr to the n cancels out, and we're going to end up with 1 over r. And similarly here, we're going to end up with 6 over r squared, which is looking much, much nicer. And to simplify that, we're just going to multiply by r squared, and we're going to end up with r squared is equal to r plus 6, which is a quadratic equation which we should know how to solve fairly easily. We get r squared minus r minus 6 equals 0. This factorizes nicely, and we're going to end up with r minus 3, r plus 2 equals 0. And that tells us that r is equal to 3, or r equals negative 2. Now, we have to ask ourselves, what does that mean at this point? What does it mean to say r equals 3 or r equals negative 2? Well, we want to go back to what we were saying r was. We're saying r is the multiplier in our solution. We're saying if we have a solution of un equal to c times by r to the n, then our possible solutions are going to be un is equal to c times by 3 to the n, or un is equal to c times by negative 2 to the n. And our c would be our thing that we have to work out from our initial conditions. But how do we know which one it is? Well, the whole point is that both satisfy. It's a wonky arrow. Both satisfy our original recurrence relation. Both satisfy our original recurrence relation, which means because recurrence relations are actually linear, everything's just being added together, this will also satisfy our recurrence relation. C times by, in fact, let's not use C at this point, let's use A. A times by 3 to the n plus B times by negative 2 to the power of n. Because if each of them satisfy, if each of them effectively all work out nicely, or if we go back up here and do a sort of rearrangement and rearrange it to un minus 1 minus 6 un minus 2 equal to 0, if both of these will make that equation 0, then them added together will also make them 0. Everything is still going to cancel out when they're added, just as if they didn't. So our un is going to be of this form. And our coefficients are 3 and negative 2 there. And then, to finish it off, all we need to do is plug in our initial conditions, which were u1 equals 0 and u2 equals 1. And let's see what happens. So when n equals 1, we're going to end up with u1 is 0, so 0 equals a times by 3 to the power of 1 plus b times by negative 2 to the power of 1, which is equal to 3a minus 2b, and that's 0. For n equals 2, we're going to say 1, because u2 is 1, is equal to a times by 3 squared plus b times by negative 2 squared. Notice the brackets are very important here, which gives us 1 is equal to 9a plus 4b, because the negative squared is positive. And this is a pair of simultaneous equations. We've got this one and we've got this one. To solve for a and b, we just need to solve them simultaneously. I'm going to call this equation 1, this equation 2. I'll take equation 1 multiplied by 2, so 2 lots of equation 1, and add it to equation 2. And that's going to work out quite nicely. We're going to end up with 6, 0 is equal to 6a minus 4b, and we've got 1 is equal to 9a plus 4b. I want to add those. I'm going to end up with 1, 0 plus 1 is 1, is equal to 6 plus 9 is 15a, and that cancels. And so we get a is equal to 1/15. Plugging that back into equation 1, we get 0 is equal to 3 over 15 minus 2b, or 2b is equal to 1/5, and that tells us that b is equal to 1/10. And so our recurrence relation, our final solution to this, is un is equal to 1/15 times by 3 to the n plus 1/10 times by negative 2 to the n. And there's a little bit of simplification you could do at that point, but I'm going to leave it there. Okay, so that's our first example. Now what I really want you to notice though, and this is really, really important, is how this rearranged form up here compares to this equation here. What I want you to notice is they are almost exactly the same. We end up with r squared minus r minus 6 equals 0. And that's what we solved to get our values of our bases of our powers. But notice the coefficients match exactly. Here we've got a coefficient of 1 in each place. Here we've got a coefficient of -1, and here we've got a coefficient of -6. The coefficients match up entirely, and this is called the auxiliary equation, and we can just jump straight to it. So that's what we're going to do for our next one. Solve this recurrence relation. Un is equal to un. Is that the same one? Okay, that's not meant to be the same one. Let me edit that slightly. So our recurrence relation is un is equal to 6 lots of un minus 1 minus 5 lots of un minus 2, with u1 equal to 1 and u2 equal to 2. This is our new recurrence relation. And so I'm going to rearrange that, and I'm going to rearrange it exactly as before, moving everything to the left-hand side, which is why in the previous videos we've been moving everything to the left-hand side each time, because it makes things much, much easier for these second order, or third or fourth order if you really want to go that far. Un minus 6 un minus 1 plus 5 lots of un minus 2 equals 0. And now we want to just jump straight to the auxiliary equation, which is, this is the r squared term. What's the coefficient? The coefficient is 1, so we're going to leave it as 1. This is the r term. Our coefficient is minus 6. And this here is our constant term, and the coefficient of the constant term is just 5. So remember, your highest value, your highest n is going to be your r squared. Your second highest is going to be your r, and your third highest is going to be the constant. R squared plus r, or ar squared plus br plus c. And then we just read those off, our coefficients directly. We get r squared minus 6r plus 5 equals 0. And the fact we can just jump straight to that makes this much, much faster, because we just factorize it. Sometimes they won't factorize. If they don't factorize, you just jump to the quadratic equation or similar. R minus 5, R minus 1 equals 0. That gives us R equals 5 or R equals 1. And therefore, our general solution is going to be the form un is equal to a times by 5 to the n plus b times by 1 to the power of n. And we just jumped straight to our general solution. One thing to note, 1 to the power of n is always 1. And so this can also be written as un is equal to a times by 5 to the n, just plus b. And now we can plug in our initial conditions. U1 equals 1, U2 equals 2. And we're going to get, about that side there, we're going to get with u1, with n equals 1, we get u1 is 1, so 1 is equal to a times by 5 to the power of 1 plus b, which is equal to 5. So we get 1 equals 5a plus b. And then for n equals 2, we're going to get 2 because our u2 is 2. 2 is equal to a times by 5 squared plus b, which is going to give us 2 is equal to 25a plus b. And now, simultaneous equations again, very quickly now in this case, because we can just say, we can just subtract the b's, so we call this equation 2, we call this equation 1, and we're going to do equation 2, subtract equation 1. 2 take away 1 is 1, 25 take away 5 is 20, and b take away b is b, and so we get a is equal to 1/20. And then, plugging that back into the original equation, we get 1 is equal to 5 over 20 plus b, and that's the same as 1 is equal to 3/4 plus b, and therefore, 1/4 plus b, and therefore b is equal to 3/4. And our solution we get, therefore, is un is equal to 1/20 of 5 to the n plus 3/4. Or, often we usually write this in front, the constant in front, un is equal to 3/4 plus 1/20 of 5 to the n. Okay, and that's how you solve homogeneous recurrence relations. Now there are a couple more awkward cases which we'll go through in the next video, and then we'll also look at solving these non-homogeneous ones. Thanks for watching, and I'll see you in the next video.